Merhaba arkadaşlar, herkes hoş geldi. Ben Altuğ Bilgin Altıntaş. Bugün İstanbul Java User Group etkinliğinde hep beraberiz. Ev sahibimiz İNG'ye teşekkür ediyoruz tekrardan. Evet, ekranda görmüş olduğunuz şu anda bizim 2019 yılında Java Community Process'in başkanı Heder Venkura'nın sahne almış olduğu bir keynote speaker'ımızı görmektesiniz. Hemen detaylara girelim. Sizlere Jack İstanbul hakkında bilgiler vereyim. Sonrasından Gregor'la sizleri baş başa bırakacağım. Neler yapıyoruz derseniz bugün olduğu gibi bir meetup'ımız var. Meetup'lar ve online meetup'lar, webinarlar gerçekleştiriyoruz. Hackathonlar, bootcamp organizasyonları, Java Day İstanbul yılda bir kere düzenlenen uluslararası yazılım konferansını destekleyen bir ekibiz. Ve tabii ki Global Day of Code-Red. Code-Red inzivaya çekilmek demek arkadaşlar. Hani normal yaşantımızda yapamadığımız aksiyonları işte test-driven development veyahut oradaki farklı programlama dillerini kullanmak, farklı algoritmalar, pair programming gibi yapamadığımız şeyleri bu inzivada yapabiliriz. Bu da haftaya gerçekleşecek. Yani Kasım ayında bir başka sponsorumuzun eşliğinde gerçekleşecek. Buna da katılmanızı şiddetle öneriyoruz. Devam edelim o zaman hızlı bir şekilde. Şimdiye kadar 7000'den fazla, hatta 7500'e yaklaşan bir üye sayımız var ve şimdiye kadar yine 110'dan fazla bu tür etkinlikler gerçekleştirdik. Tabii yüz etkinliklerin değeri bir başka. Devam edelim. Evet. JAC yani Java User Group İstanbul olarak Java Community Process ve Eclipse Foundation'ın üyeleriyiz. Buraya açık kaynaklı projelere katkı vermeye gayret ediyoruz. Ama tabii bu süreç çok da hızlı gitmiyor ama yavaş yavaş güzel noktalara ilerliyoruz. Katkısı olmak isteyenler varsa gelebilirler. Dediğim gibi non-profit bir organizasyon, herkese açık. Dediğim gibi haftaya arkadaşlar 5 Kasım 2022 tarihinde Kod-Red etkinliğimiz olacak. Kod inzivaya çekilme. Bunda İstanbul'da gerçekleşecek. Yüz yüze bir etkinlik olacak. Sonra 25'inde Venkat. Venkat bizlerle olacak ve Java'daki yeni özellikleri bize online çevrim içi bir webinarda bizlere anlatacak. Ondan sonra etkinliklerimiz var. Bunun için Meetup sayfamızdan veya Twitter'dan bizi takip edebilirsiniz. Java ile ilgili son dedikoduları, son gelişmeleri duymak için ayda bir kere düzenlediğimiz, bir kere yayınladığımız daha doğrusu bir podcast serimiz var. Buna Spotify, iPhone, iTunes'tan erişebilirsiniz. Verdiğimiz hediyeler var. Burada da JetBrains'e teşekkür ediyoruz. Her ay Twitter üstünden bir hediye çekilişimiz var. İNG'ye ve diğer sponsorlarımıza çok çok teşekkür ediyoruz. Eğer Java User Group İstanbul'a katılmak, daha fazla bilgi almak, katkı vermek isterseniz Slack kanalımıza bekleriz. Evet, burada bir e-posta ile ulaşmak için e-posta bilgimiz var ve Twitter'dan da @jack_İstanbul'dan bize ulaşabilirsiniz. Şimdi sizleri konuşmacımızla baş başa bırakıyoruz.
Thank you, everyone, for coming. My name is Gregor Pivovarek, and I've been here multiple times because I work at Hazelcast as lead architect at the office of the CTO. We don't have the CTO at the moment, but I still work at their office. I've been here for multiple times, but the COVID made things a bit different and difficult, so I'm glad that I can finally join you here at part of the community event. Being lead architect means that you probably assume that I do a lot of coding in PowerPoint, and I do, and it's nice because it always compiles. But this also means that I get kind of very broad overview over products that are being developed at Hazelcast and what those products are, how they are getting developed, and I have influence on that. So I thought I could give you a short introduction to insight in what we are planning, what the technological revolution Hazelcast is going through, and give you some insights about what we are experimenting with, because there are some crazy ideas we are playing with, and Hazelcast 6.0 could be totally different from what we have right now, in a good sense of that word. So Hazelcast was born here a very long time ago. So I think the first lines of code appeared in 2008. That code, though, wasn't public, and the company was actually started by a Turkish folk living in the US. And it indeed started as a cache. It started as this Java-friendly cache. And at that point in time, it made a lot of sense, because 2008, what kind of hard drives were available out there? Those were mostly old-school hard disk drives that had all those physical parts moving, that would needed to physically move from one location to another in order to be able to read some data. That was painfully slow. But all the data that you would keep in memory, in RAM, that was orders of the access to that, the latency was orders of magnitude faster. So that's how in-memory computing and caching started blooming, because there was a huge demand on that. However, things change over time. And at this point in time, 2022, we are having this SSD hard drives, NVMe, and the latency between RAM access versus NVMe SSD done right is not that significant anymore. So we needed to catch up with all those things that's been happening out there. But it all starts with a cache. And I remember myself that when I was a student that's a long time ago, 12 years ago, 13, no, 12 years ago, 11, long time ago. I attended one of the conferences, and I remember there was a Hazelcast booth over there. And one of the folks grabbed me and told me, look, give me 5 minutes of your time and I will give you a t-shirt. And I was a student at that time. Don't judge me, but 5 minutes of my time for a free t-shirt, that sounded like a very good deal. So I did that, and the folks showed me basics of Hazelcast, which means they created one map, second map, so one Hazelcast instance, second Hazelcast instance, everything in a plain, simple Java code with one dependency in Maven POM XML file. Those somehow magically clustered and started working together. But I would say that 5 minutes were well spent. I was pretty impressed. But that's not that impressive anymore. So from a simple Java cache, Hazelcast started evolving into something so-called IMDG, which is, well, it's not cache, it's an operational in-memory computing platform, whatever that means. So it started getting polyglot and started supporting way more things than just boring puts and gets. And it was absolutely necessary because, for example, imagine a simple scenario in which you have a cluster of 50 nodes, 100 nodes. Each one has, hundreds of gigs of data. So suddenly you want to process the data somehow. So, well, it's a Java application. You have a Java client. What you can do, you access your map, you do a for each. You provide the clarity of what you want to do with that, and then you put this back into a cluster. And there's a problem with that, because if you actually do something like that, actually you might not have enough memory to process on your machine, data stored on 50 nodes. Keep in mind this all needs to get transferred via network as well. So the best possible place where you can make this kind of computation is where the data sits. So that's how we slowly evolve in the direction of in-memory processing platform, which means that suddenly once you had all your data in the cluster, you were able to do a bit more than just put it and get it. And if you look at what this IMDG stands for, it's actually in-memory data grid. In-memory underlines that there is no persistence, and it's supposed to underline that it's simply very fast, because it's marking that it's not hard disk drive, but RAM memory. Storage computation, you already know. It's no longer just a key value store, but something that can do computation on top of data. And grid effectively means that it's just something that can be clustered and work together, where you have multiple processes working together. So the way it looks like from the outside is that you might be putting something into one continuous map. But what's actually happening is that you have multiple nodes. Each has their own subset of data. They own their own partitions. They manage backups, and so on. So this data is not replicated one-to-one, but partitioned. And at this point, usually you might be thinking, let me help you put it into its context. So where in the architecture you would like to put that. And normally, we'll put that thing as Hazelcast. So this sounds like easy choice, right? Because, here's your some data store or some source of data. Here's Hazelcast, but it starts getting a bit difficult if you start thinking about how to implement proper access to that. Because let's say you want to sync two systems that communicate over network. How would it look like? Imagine there is some request coming to your application, and you need to write an if statement. Nothing difficult. So you check if this data is in Hazelcast. If not, read it from a database or something else and put it into Hazelcast. Okay, easy. What if you do a write? So there is something that's coming into our application, and that's supposed to result in a write to a data store on Hazelcast. Okay, so you are like, okay, I'll write to database and Hazelcast. But if you start thinking about what if we would like to do it the other way around to be a bit faster? What if we like to write to Hazelcast and to a database? And if you start thinking that network can fail anywhere in those processes, suddenly it's becoming difficult because it's about dual writes and synchronization of two independent systems. And this is a non-trivial problem. So luckily, there are a bit better solutions to do that. So you don't always need to do it the same way. And one of the most obvious ones is a pattern called read-through. So instead of treating those systems as two independent systems that need to be manually surrounded with if-else statements, you can let Hazelcast read data for you. So instead of you being responsible for managing cache misses, Hazelcast can do it for you. So if you're hitting Hazelcast data is not there, it will backload the data into Hazelcast and return it back to you, which makes it a bit easier to manage inconsistencies. This obviously works the other way around. So if you are worried about consistency, you can do a write to a Hazelcast first, and then let Hazelcast follow up with a write to a data store. A bit less complex. But you might be thinking, Greg, I put my Hazelcast in there because I wanted things to be faster. And I might not be a computer science PhD, but if I'm writing directly to a data store, and if you put a Hazelcast in between, so I write to Hazelcast that Hazelcast writes to data store, it's probably going to be slower than if I would be writing directly to the database. And yes, that's true, because obviously that's a trade-off between, let's say, simplicity and potential performance. But if you are really about lower latency, then and that kind of stuff, you probably want to enable use the pattern called write behind. And in this pattern, we write directly to Hazelcast, and that's where we stop. We let the Hazelcast cluster decide when is the right moment to flash all the changes to the database. Obviously, there is a risk that something might not really work out along the way, but that's another trade-off. So none of those are superior. At the end of the day, is about understanding your use case and what trade-offs are perfectly acceptable and which are not. I'm showing you those pictures just to give you some potential indication, let your imagination work and where this could potentially sit. Some people are saying, okay, but what's the use of a cache that's accessed over a network, right? Because that will be slow because you always need to pay the network cost. For those people, we can always have a cache in the cache. So if you are okay with eventual consistency, but if you are okay with your eventual consistency being a bit more on the eventual side, you can obviously rely on the concepts like near cache, which means that most commonly accessed data would be actually cached on the client side. So if you want to access some subset of data, the data that's hot, you'll be getting that directly from your client cache and not from the cluster, without paying the cost of a network trip. So we've been living like this happily for a while, but then things changed. Things like cloud, containers, Kubernetes started changing the context and basic rules of the game. And some things became more difficult. I mean, even some simple things, some things became simpler, some became harder. So let's start with very trivial stuff. We are working with containers. The way you would configure Hazelcast in the past, it's mostly about file. You can use XML file, you can use YAML file, but the thing is, and it was convenient. So if you are used to a typical setup where you have, some virtual machines, you have physical boxes, probably it's not the difficult thing to provision, a configuration file. But once you are in the world of cloud, containers, serverless, suddenly, if it turns out that you need to craft your own XML file just to be able to, flip one switch and, provide it to a Docker container or to a ECS on AWS, no, that's not rocket science, but it's pretty annoying. Another thing is all of that nice compute capabilities of Hazelcast, all of those patterns I've showed you, those write through, read through, right behind, they assume that Hazelcast is capable of running some code, executing it, and putting stuff into the database or reading from it or from any other source. There's also a case if you want to rely on a performance serialization protocol, you need to write your own serializers, which means you need to deliver another types of files into Hazelcast for it to work smoothly. And again, this is super annoying because now you need to figure out how to craft your jar file, how to make it available on the class path, and hope the thing goes well. Because if it goes wrong, you might need to do some class loading debugging, which is not fun. Especially if you are a Golang developer or Python developer, and suddenly you need to write Java code to be able to run compute on top of Hazelcast. Another thing is autoscaling. Suddenly, there was a promise that cloud will allow you to fire all your ops teams and will be way cheaper because you can just do a few clicks and your infrastructure will be running. But suddenly it turned out that you are one click away from going bankrupt if you forget about a couple of instances of bigger machines on AWS. So suddenly autoscaling became something that people are after. And if you start thinking about it, the longer you think, it's harder to implement right. Because you might be thinking, okay, autoscaling, easy. You look at the metric of how much memory is consumed, and then make a decision, upscale, downscale. But it's a bit more tricky than that, because you might be running streaming jobs. You might be running operations that are compute intensive. Or perhaps you might be facing traffic that's changes a lot. So 1 second you have 0 requests, second you have 10,000 requests, and third second you have nothing. And if you start thinking how to accommodate all of that, you probably end up at the conclusion that this is a difficult problem to solve. But if you want to autoscale it on your own, the problem is on you. Another thing, this is quite interesting, which cloud changed, is that sometimes you need to deal with really funky resource allocation. So the way the Hazelcast works internally is relying on so-called SEDA architecture, state event-driven architecture, which is a very smart term for just a couple of thread pools connected with queues. So if you and put something to Hazelcast. You have a thread pool responsible for reading from a socket. It's forwarding it to another thread pool, and at the end of the story, there's a thread pool threads that are responsible for writing to a partition. And this is, well, that used to be a state-of-the-art, but there's one problem. How do you tune it properly for your host? Usually it depends on multiple factors. I need to figure out what's the right size of the network pool. What's the right size of the pool, the partition? How are they related, and so on. And this has become difficult. But it becomes especially difficult when your host is returning, telling you that you have just one CPU available. Suddenly, everything can go nuts because no one assumes that, for example, Hazelcast could be running on a host that has just one CPU available. But in the cloud, Kubernetes is perfectly normal because we logically restrict resources. So suddenly you need to get ready for that as well. But one of the biggest challenges for us is that Java is no longer a main choice. Because when you think about cloud containers, Kubernetes, you think Golang, you think Node.js, you think Rust. Java is rarely the language of choice. But in order to be successful with Hazelcast, it turns out you need to deal with Java code a lot, even if you are not a Java developer. So again, this starts as simple things. If you try to flip a small switch in Hazelcast, running in a Docker container, you would need to figure out how to craft your XML file, mount it, and make it available. Again, annoying, boring. So perhaps you can do that using an end variable, because it's super easy interface that allows you to interact with stuff running in containers. Another thing, we made a huge effort to be polyglot first. And it starts with serialization. Because most of the time when you need to upload classes to Hazelcast, upload jars, is because you need to have performance serialization. But again, this is boring. We don't want to make people write it by themselves. So we came up with a new serialization mechanism that's able to do that for you. So starting in Hazelcast 5.2, which will be released, by the way, in a week from now during KubeCon, you'll be able to take your Java class or Golang struct or whatever the analog, the alternative is in a language of choice, and just save it to a Hazelcast using compact serialization, and that's all. No longer need to write your own custom serializers and upload them to the cluster. Secondly, all those compute capabilities, like processing of the old items in the cluster, there will be no longer need to write custom Java code because we have full-blown SQL engine. It's not fully ready; it's already available, but it's getting a lot of improvements. You'll be getting a lot of improvements in every new minor release. Another thing is this read-through, write-through. In order to be able to do that, you need to write Java code. But what would be better than not writing Java code? Well, not writing Java code. So in 5.2, you will get things like zero-code map loader, which means you'll be able to declaratively provide configuration that, let's say, I want to read this from that particular MySQL instance, and that's pretty much all. And it will work right away for you. So as you can see, that's how a simple SQL browser looks like, which is a part of the console. Good. We have also Hazelcast JDBC. So it's hopefully at the end of the transformation, you should be able to fully enjoy Hazelcast without writing Java code. But if you want, you still can. So, but Hazelcast IMDG is, when people mention Hazelcast, they usually mean IMDG or the cache. But we've had another product on the side that's been running for a while. It's called Hazelcast Jet, and it's a real-time stream processing engine, which is pretty impressive. So and the interesting part about that is that Project Loom nowadays is a hot topic because it was finally released as a preview feature in JDK 19. But when the Hazelcast Jet was developed many years ago, no one dreamt about Loom making its way to Java. So folks that were responsible for that needed to write pretty much their own engine, which is similar to the way the Loom works. And you can read more about that in this particular white paper. And we publish all the design docs. We try to publish the architecture documents. So even if that's not something that you can use in your project, that's still something you can simply learn from, because there is value in going through that and understanding the trade-offs and how the decision process looked like. And so we've had this Hazelcast, AMDG. We have stream processing engine. Stream processing engine is depending on Hazelcast. It's using it internally. So at some point, someone realized, hey, let's put those things together. Because if someone wants to use Hazelcast Jet, they still need to deal with Hazelcast. And it was a pretty tricky move, because now we could go to our customers and tell them, oh, so you are using Hazelcast 5.x. Do you know you have stream processing engine already available for you? And this allows you to do interesting stuff with the data that you have in Hazelcast already. So it's not just put, get, and process, but you can analyze this data in real time and use it for interesting things like the examples that you see right now. So the use case I implemented a long time ago for a Polish telecom was that they wanted to leverage one interesting fact. People procrastinate. People procrastinate, and when people were driving abroad for their vacation, they wouldn't pay for their roaming packages to get internet or just phone packages abroad. So what they did is they were analyzing in real time how SIM cards, MMS-ISDN numbers reconnect to BTS stations. And they could notice patterns. If they saw that someone is going towards the border, they would issue them in real time a marketing event, marketing text message saying, oh, there is just you are one click away from getting your roaming package if you've forgotten about it. And it allowed them to boost their revenue a bit. I don't know how much, that's confidential data, unfortunately. So that's how we arrived at Hazelcast 5, which is this Hazelcast platform, not IMDG, combining in-memory compute with stream processing. So if you're on 5.x and if you are using it as a cache, you're probably missing out on quite an interesting capabilities. But we took it even further. So the issue was that in order to be successful with Hazelcast, you still need to answer quite a lot of questions and tune some knobs. You need to make a decision of, for example, how many nodes do you want to have? What's the size of each node? Do you want to have asynchronous backup or synchronous? How many backups? Do you want to have persistence on? Do you want to have HD memory on? Do you want to have hot restart on? Do I want to enable one replication? One-way, two-way, with batching, without batching, and how do I auto-scale? At the end of the day, there are questions that you need to answer. We are not able to answer for you because it depends on a particular use case. But we still tried to provide the cloud version of Hazelcast that's opinionated and as easy as as possible. So what we try to do at Viridian is that you can just create your cluster and think about data as your abstraction. You don't think members, you don't think backups, you think data. So, and by the way, it's for free, up to 1 gigabyte for some time. So if you can register just with your GitHub account, few clicks, and you're right away. And you don't need to worry about how many members do you want to have. You don't need to worry about turning on backups or something else because it's all managed for you. You can only worry about data that you put inside. So that's the newest thing. We released it not that long time ago. It's still in beta mode, so it can be rough around the edges, but you can still give it a try for free. I think I already told you that. So again, once in this nice picture where there's Hazelcast cluster inside, there are some things going from the left side, there are things going out, there is a business value going out somewhere, and there is an enrichment from here. We forgot about use case like, what about we would like to stream the data that's actually already in Hazelcast? So we've added that. So we've added change data capture, which is a hot term recently on the IMAP itself directly. And we started experimenting with another approaches. So hardware got cheaper, hardware got better. Perhaps the new ways of the better way of running Hazelcast would be to use the concept of called tiered storage. Tiered storage introduces tiers of memory. So far in Hazelcast, you could keep everything on RAM, and that's pretty much it. You could have persistence, but persistence was mostly used for the sake of recovery and not for ensuring proper persistence. And with the tiered storage approach, there are two tiers of memory. There is RAM and hard drive, and pretty much data can spill over to the hard drive. And this is nice because suddenly the limit of how much data you can put into a single member goes up multiple times. And that's something that will be available as a preview in 5.2 in a couple of days, and you can simply try it out. And now is the last part of the presentation, which means I'd like to give you a short teaser about what we are experimenting with. So a couple of minutes ago, I told you about the staged event-driven architecture. Multiple thread pools connected by queues and how difficult it is to properly tune that, and that weird things can happen when you have just one CPU. So what we are experimenting with is to rewrite all of that using thread per core approach. What is that? So the problem with SEDA architecture is that it's hard to tune and it wastes a lot of time on synchronization. Because, well, if there is multiple queues along the way, there needs to be time spent on synchronization. The more cores you have, the more threads you have, the bigger contention and different bottlenecks appear. Thread per core is a very simple idea. It means that you have the number of cores matches number of threads, and each thread is doing all the work. Everything from reading from a socket to rewriting to a partition. Thanks to that, and every thread is assigned to a particular partition, which means that as long as the one core is doing all the work, it doesn't need to use any synchronous code. I mean, concurrent code and then synchronization, which means it will be blazingly fast. And if you mix that with asynchronous I/O, perhaps we could end up with something that's storage first and thread per core with throughput and latencies way better than existing product and being persistence first. And you already have some proof of concepts, and it's very promising. However, again, probably our legal team would advise me to tell before the presentation that I'm lying. And in order to be able to be very efficient at this kind of architecture, you need to make sure that you are saving pretty much your computation and garbage. So pretty much all that code will need to be allocation free from the Java perspective. But another thing that would be cool to have is a schema. If you have schema first, you can control the layout of how you put data into memory. So now technically we have a schema, but it's a schema that appears after you've put something into Hazelcast. It doesn't change the layout in memory. But if we go schema first, For example, we can reorder fields. We can figure out the optimal layout for this particular data that's being stored. And that's something that we are experimenting with with next version of Hazelcast. So, for example, someone is sending. Imagine you are sending a class that has 8 Boolean fields. Why create 8 entries if you can use one integer to represent all of that, or short, depending on the number of fields you have in your class. So those are kind of the experiments we are trying to run. We'll probably try to make it available as soon as possible in the cloud, because it's probably going to be in the cloud, and there will be snapshots of that. But since this is a highly experimental project, probably we'll be shipping. We want it to be cloud friendly, so we'll be experimenting a lot with our cloud team and trying to make sure that it's truly cloud first, and that cloud is not just an afterthought. And that's pretty much all that I wanted to show you today about Hazelcast, the future, and insight into what's been happening during, last weeks and last couple of years. So thank you very much. And after the break, I will have a chance to show you a bit more technical stuff. So we'll do the opposite. Less slides, more coding. And the topic is comfortable future. It might sound unrelated, but I'm sure you will find some references, because actually there's a lot of interesting things about multi-threading and how comfortable future approaches threads. So thank you very much, and I think it's time for a break.